Right. Hello, everyone. My name is Martin, and I will talk about large volume data analytics on the Typesafe Reactive Platform. So the importance of analytics and processing of large volumes of data is increasing. It offers many business opportunities, including mining hidden knowledge and patterns, recommendations, classification, predictive analytics, or being able to run processing faster on large amounts of data. But many companies, they don't store history of the data, so they do destructive updates on the database. They use analytics tools with poor scalability and integration. They use often manual processes, so the iterations are very slow. It's not suitable for large amounts of data. One option how to process large data volumes is to use parallel programming. And there are many different approaches to computing in parallel, each with different API, programming, memory, and communication, and importantly, coordination between the processes. I'll today talk about threads, futures, actors, and data flow model, but there are many more that exist. Another level is distributed computing. It means there are multiple machines cooperating and trying to reach a common goal together. Distributed computing is it's not always the solution. It's actually often misused for problems that could be solved more easily and actually faster on a single machine. It also introduces many new complexities that may not be necessary, including having to worry about things like time and order in distributed environment, message delivery, network latency, consistency, failures, and the deployment becomes more challenging. Companies including Baidu or Google reportedly used optimized single-threaded algorithms or high-performance computing utilized to run on GPUs to run their most complex algorithms and their most complex processing. The most challenging part really is to implement an efficient algorithm in the chosen model. The complexities of the distributed environment include that network nodes and other components may fail independently. One of the worst cases is that a network fails within the I think my
battery or something?
No, it should be. Yeah. Sorry. So one of the worst cases, one of the biggest complexities is that the network fails between the nodes, but the nodes continue to function in the system. Network partitions like this, they can happen and they will happen, as demonstrated on this report from Kyle Kingsbury and Peter Bayliss. The correct handling of those scenarios actually is crucial. But even mature technologies such as MongoDB, RabbitMQ, RAIC, Redis, Elasticsearch, or MySQL, they cannot handle those scenarios properly. They often lose acknowledged writes, or when reading, they return writes that should have never occurred. So it's really, really difficult to work with distributed systems. However, positive impacts of distributed systems include availability, resilience, geographical distribution, ability to run on cheap hardware, scalability, handling of really large data sets that just wouldn't fit on a single machine. Distributed systems are about trade-offs that need to be carefully considered before using one of them. Even with all the aforementioned complexities, some distributed systems show amazing performance. One of the examples is distributed data processing framework Apache Spark that won the Daytona Gray Sword of 100 terabytes. Another good example are distributed database. But when developing No, I don't think so.
think it's not a problem of adapter. I think it's, we can try, but I don't think if it's a problem of the adapter. I think it's a problem of the
computer.
It ain't working. We can try, but
Of the computer.
No, the projector maybe. I'm getting the signal. Yeah, maybe. No, no. So sorry. You need HDMI? No, thanks. It's.
I restarted the computer to let's see what happens.
Okay. IT guy is coming. I'm still getting some. Yeah.
Sorry? We can try, I guess. I'm not sure what the issue is. It's online, yeah. Or maybe I can use this machine. Can I use this machine?
You can use it if you want.
Well, I can try. Presentation's online, so I can try.
Okay, sure.
We have a machine here, we can try this one.
I think it's probably okay. You can use it.
Can you stay here? I will need to move one of the screens as an external monitor. Can you set it up for me?
I think you can do it by this function buttons. Let me see. I think it's one of these.
What account?
A second.
No, I don't want duplication.
It's no replication.
No, I want an external monitor.
Okay.
Right, can you help me logging in? I cannot present with speaker notes. I really need to present with speaker notes. It just does not really.
Except for the.
Yeah.
And you can move it to the other side.
Sorry?
You can move the window to your side. That's what you need.
I can open it in two windows, I guess. How do I open another window? Now how do I? How do I move this to the?
Did you? No. Yeah, that's right.
Present.
You can do present for now.
Yeah.
Maybe it's the other way. Move this to the other side.
I want this one on there. Here.
Oh, sorry.
And then the other one back here.
Okay. And then oops, sorry.
But this won't work anyway because I need to change both of them. I need to the clicks to work on both. I don't think clicks to choose the slice both of the strings and everything I do that. Yeah. Show which one is my machine.
Forwards and backwards at the bottom left hand corner.
It ain't count. Maybe I did right. It ain't counted. I don't know why.
You see there, can you move it back to my screen? Just minimize it and move it back.
I'm going back to reception again. I'm trying.
Right, sorry for the inconvenience. I think we can continue if it works. So as I mentioned, distributed systems are about trade-offs, so we need to really decide if we want to use them or not for a given problem. When developing application in distributed system, we need to focus both on optimizations on a single machine, so on things like proper data structures and algorithms, register and cache locality, in-memory and disk storage layout, garbage collection optimizations, parallelization and concurrency, indexes, probabilistic data structure and all that. And at the same time, we need to focus on optimizations on the distributed system level. So things like data locality, network traffic, handling of failures, and so on. Data processing pipeline is not just a single algorithm. We need some framework where we can run all our analytics and machine learning. It must cover the whole life cycle of data, so from getting the data from some external data source to processing of the data, running machine learning queries, training algorithms, training models, and storing the data. So there are many tools that need to work together to achieve this, from data processing frameworks that we will talk about today, to data stores, integration tools, distributed computing primitives, deployment tools. Sorry. Shuts down once in a while, every few minutes.
Really shuts down?
No, it does not shut down. We tried to multiply that already. Never happened before. You know,
Of course it never happened before.
the machine should go on. The battery is full.
Yeah, but it doesn't show a picture when I remove it. So.
Yeah, no. That's the issue.
You can't pay this machine and use that.
You can try that, I guess.
Yeah. Do I use this software? Or is it online?
It's online. We tried on this machine and it didn't work.
Yeah, okay.
So let's try that.
Yeah, all right. Sorry.
Also, my presentation will probably take a bit long.
Oh, it's okay. No problem. We're sorry.
Thank you for your patience. There will be an awesome party later, so. And this is an anecdote, you can tell. It's all good. So move the mouse once in a while.
Plug the Thunderbolt in last, the VGAs connect the Thunderbolt first, and then the Thunderbolt go out.
Yeah. No fucking way. This machine does exactly the same as the other machine. So I'm...
Went black.
Okay, then it's definitely not the machine, and it's something underneath here. Can you also do it without?
Just turn your machine around and just talk.
Probably.
Okay, then probably everybody in the back seats want to move forward. So then if that is a possibility.
I need to see the screen as well.
I think you can just see the screen, then you just hear.
It's not worth it.
No, that's not working. Okay.
Without
Do you have the telephone number of the AV guy in your phone?
just the summary.
Tommy had
You just map reduce
0031.
Wait. Work.
Your machine is all black now. Hopefully you did not read it.
0031.
Yes.
61 09 19 070.
This is just ridiculous.
It is.
No, I've seen that before on AV machines that don't give out correct DDI.
Can you just remove the notebook and try it again so that the notebook, that the Mac is not on this notebook, because that might be also a problem. Hello, this is Diana speaking from the violin Saal. We have a problem here, a technical problem.
There would be a problem.
Thank you.
It's on my Google Docs only. Share with everyone.
No, he's probably presenting something. They told me that they will send somebody. Yay! AV guys is coming. So we will greet him with a big applause when he's in here, right?
So 3 more minutes.
Yes, 3 more minutes. Run.
So it's not just data processing frameworks that we'll talk about most today, but also data stores, distributed computing primitives, deployment tools, data analytics tools, and so on. And most importantly, there are many technologies in each of those categories with different levels of maturity, different use cases, different advantages and disadvantages. So we always need to pick the best pipeline or the best combination of technologies for our use case. Traditionally, data pipeline used to include a monolithic application and often a relational database with full ACID properties, representing a shared mutable state. Destructive updates were done, causing the history of updates to be lost. Shared memory, concurrency, and other complexities were handled for the developer, which is good because they didn't have to worry about them. But sometimes when the data scale, when the throughput scales, we want to pull those complexities and handle them ourselves at the application level. So some of the other solutions include CQRS, where read and write concerns have separate technology and scalability, or large batch pipeline, where we use large-scale database such as HDFS, and then we use different technologies to pull the data from the database. Or Lambda architecture, where we add a stream or a speed layer next to the batch layer, which we can use to pre-process some answers to some queries in near real time, or so-called Kappa architecture, where we use database which can handle large amounts of streaming data, and we can then query the data, replay the data, and integrate with other databases, each with different guarantees and different data model. But importantly, there's no one-size-fits-all architecture or technology. There are common attributes. For example, we store all the data, we don't throw away data, and we use multiple technologies in the pipeline. Sometimes there is some sort of duplication or denormalization. We built a system called Muvr, which uses data from devices such as accelerometer in a watch or heartbeat monitor to classify exercises in near real time. The architecture is very similar to what we mentioned previously. So the blue box is streaming. It uses Akka Cluster to distribute domain, and Akka Streams for data transformations within that distributed domain. And the pink box is batch layer, which uses Apache Spark and does more expensive analytics queries and machine learning algorithms, such as training of machine learning models or suggestions. And this is often done for each user individually, so it processes large amounts of data. I will talk about each of those technologies, and I will mention some of the attributes, some of the important characteristics they have with regards to large volume data processing. So neural networks are one of the machine learning models, one of the machine learning techniques that we use. The reason I will talk about it is because it's very powerful. It can approximate and generalize any function, and it's computationally expensive. And most importantly, it can be modeled using different approaches. So we can use this to demonstrate some differences between programming models and guarantees of different approaches. So the single computational unit is called Perceptron. It has multiple inputs that can be modeled as vector y, and each of the incoming edges has a weight which can be represented as a vector w. It computes a sum of products of those two vectors, adds another number called bias, and runs it through an activation function. In this case, the function is a sigmoid function. But most importantly, we can connect those perceptrons into a network. The most difficult part of this is training of the network, so setting of the weights, setting of the biases, and the topology. There are many algorithms how to achieve this, but we will only focus on forward propagation through a trained neural network. Sorry. This is how a network representing XOR function may look like. So the numbers on perceptrons are biases, the numbers on edges are weights, and what it does, it has two inputs and a single output. So what it does in the layer of perceptrons, it calculates the sum of products of those two vectors, so weights and biases and inputs. It adds the bias, runs it through the activation function, and produces an output which is then used as input to the second layer of perceptrons. And the final output in this case is 0.9995, which is very close to 1, which would be the expected result of XOR for this input. Now let's model this using object-oriented sequential Scala. This code is nowhere near ideal, but we will use it to present some concepts. So we have an edge, class representing an edge, which has a mutable state called weight, and it has one method, run. The only thing it does, essentially, it receives an input, it adds weight to it, and sends it to the perceptron it's connected to. The perceptron itself will look like this. So it has also a mutable state called bias, inputs and outputs, and then it has feature and weight vectors. What it does, it receives each number from that vector, from that input vector and weights separately. It forms that those two vectors internally as a mutable state. And when all inputs available returns true, so when the whole vectors are available, it produces the activation function. Then we build this network. So we build those perceptrons, edges. We use add input and add output functions to connect them together. And then we read a file and treat each line from that file as an input vector. For simplicity, we'll use just this network, and the input vectors will be always three same numbers, so 0, 0, 0, then 1, 1, 1, and so on. The output should look like this, so monotonically increasing sequence of numbers. But we want to utilize our multi-threaded CPUs. We want to parallelize this. One of the options would be to use Scala's futures, which is a very nice, convenient way to work with parallelism. But the simplest option is really to use parallel collection. So we just add the .par method call, and it parallelizes the computation. But as you can see, it does not produce the outputs we would expect. It just produces two outputs, sometimes 1, sometimes 0, and they're not correct. And this is because we access shared mutable state from multiple threads. They can interleave in more than one possible order. So when the perceptron is checking if we have all those three inputs available, there can be a context switch at any point in time. So it misses that condition, and it will never produce any output again. One of the solutions is to use some sort of synchronization, which, however, can be expensive. So another solution is to use functional programming. The perceptron activation function is exactly the same as previously, but we work differently with the network. We use this feed-forward function, so we take the network and we fold over it. The first input are the input features, and by folding, we use outputs of one layer as inputs to another. So just a simple fold computes the function of the neural network. Then we construct the network by partial application of those activation functions, so they are just functions from inputs to outputs. This is a very simple solution, but most importantly, there is no mutable state, so we can run this in parallel very efficiently. Another approach how to model the same scenario is using Akka. Akka is a framework for truly concurrent and distributed systems, which uses actor programming model. Actor processing message is single-threaded, so it can contain mutable state and it can mutate state safely. Actors can essentially just asynchronously send messages, create new actors, and change behavior for next message. Akka is very powerful, but many people don't use it correctly. They use it as object-oriented programming and method calls, and we will see very soon that it's not just possible to use it that way. This is how we can model perceptron using typed Akka actors. So we just, instead of standard untyped Akka, we don't create classes for actors, we just specify behavior. In this case, it's the feed-forward, it's the behavior. It has a few parameters, And as you can see at the end of the feedforward function, it returns feedforward again, which specifies the behavior for next message. So we change state by returning the same behavior with different parameters. But other than that, this is almost exactly the same as the object-oriented implementation. Again, we receive each number from those input vectors separately. We form the vector internally. And when we have the whole vector available, we calculate the activation function and send it forward. But if we run this, the result will not be correct. And when we check how the values of input vectors look when calculating the activation function, you can see it's not all the same numbers. So we would expect 0, 0, 0, then 1, 1, 1. But it's not the case. They are somehow mixed. This is because in Akka we don't synchronously call methods, but we asynchronously send messages. So this Perceptron can receive multiple inputs from a single edge and no inputs from another. Or it can receive inputs, even if it receives inputs from all the 3 edges, they can be in different order. So it's still a different vector, therefore the result is not correct. This is because of order in distributed system. Sequential programs always have one total order of operations, but there are no such guarantees in distributed system. Akka, for example, guarantees that messages from one actor to another will be ordered, but other than that, there is no such guarantee. Another important concepts are delivery guarantees. Generally, in distributed system, we only have at most once delivery guarantee. This is also the default in Akka. That means that messages may be lost due to network or node failures, but we also can achieve at least once delivery guarantee, which can be also achieved in Akka. It means messages may be duplicated, but they're never lost. The last option is exactly once, which can be achieved, but it's very, very expensive in distributed system. The core of the problem essentially is that no acknowledgement of the message before processing the message, and then a crash can cause data loss. An acknowledgement after processing the message, and then a crash or lost acknowledgement can cause duplication, duplicate delivery. This is illustrated nicely on the 2 armies problem on the picture, which proves it is impossible to design an algorithm for agreement on value using communication over unreliable channel. Similarly, the FLP theorem proves it is impossible to reach distributed consensus with at least one faulty process. It's achievable, both are achievable in practice, and also some operation attributes help avoiding those complexities. For example, at least once delivery guarantee works very well with idempotent operations, because even if the messages are duplicated, the idempotent attribute of the operation ensures that the result stays the same. So back to the neural network example. The picture shows the order of method calls in the sequential object-oriented implementation. It's one total order of operations, always the same. In Akka, however, we don't have that guarantee. The only guarantee we actually have is that the question mark +1 layer of messages happens as a result of the question mark messages. So there's some causality between the layers, but other than that, we don't have any ordering guarantees. This is not issue with Akka. It's exactly how we would expect the programming model to work. It just requires a different way to approach problems. So one of the solutions could be to add some IDs to those vectors and wait for the whole vector, or pull instead of push, or send the whole vector instead of sending each number separately. Now, we can quite easily encounter a scenario when one of the actors dies. That can happen. What happens in our naive implementation is that the network still continues to process inputs, but the outputs are not correct because, again, only part of the network processes messages, and the dead actor just throws them away. So this can also be solved by defining proper supervision strategies and error handling, but it requires work from the developer. So actor model is very flexible and powerful to express the algorithms we need. But we need to do a lot ourselves manually. Akka shines the most when the system grows past one single machine boundary. The example on the pictures is called neural network model parallelism. The model is too large to fit on a single machine, so we need to distribute it. We need to distribute it to multiple machines. It's very convenient to work like this, but it has some performance impact. So we will use Akka Cluster to maintain the state of the cluster, and Sharding to distribute and manage the life cycle of actors for us. From programmers' perspective, we want to co-locate entities based on communication patterns. utilize machine locality can be done using those ID extractor and shard resolver. So we define function that specifies where each actor will live. Cluster sharding is essentially horizontal partitioning. It splits the data, in our case actors, into independent partitions, so each actor only lives once somewhere in the cluster. The picture on the left shows how we can, one option, how we can co-locate those actors, so we do it per layer. And the other option, we do it differently. The bold lines represent communication patterns across network that are most expensive. And as you can see, the left picture has much more of them, so we probably want to do the right one, which is more efficient. This is how we can implement it. The code is actually very similar to the previous implementation. We use untyped standard Akka, but the only real difference is that instead of sending each message to individual actor ref, we just send a message to a shard region. And shard region takes care of delivering that message to the correct actor somewhere in the cluster. And when we run this code, we can easily encounter a scenario where one of the nodes becomes unavailable. Failure detection itself is an interesting problem in distributed system because it is incredibly difficult to distinguish between a failed node, a network failure, and just high latency or the node not responding because of high amount of work. Failure detection is usually done using heartbeat messages and some timeouts. Akka, for example, uses phi-accrual failure detector. If the node is unreachable, we need to recreate the actors that lived on that node somewhere else so we can continue processing, so we can continue working. Akka Cluster sharding can actually do this for us. But as you can see, it will start throwing null pointer exceptions. This is because if you remember how we initialized those actors, we used add input and add output methods to initialize their state. But when the actor is restarted, it does not have the knowledge of the state because it did not receive those previous messages. So when it receives message, it does not know where to send the result, so it throws null pointer exception. One of the solutions to this is called Akka persistence. So we use event sourcing of the events. We store the updates to actor state in an append-only immutable journal of facts backed by a distributed data store. We can then create snapshots or simply replay the messages when the actor state is being rebuilt. The changes in the code are actually, again, very, very small. So instead of actor, we extend persistent actor, and instead of implementing one method, receive, we implement two methods, receive command and receive recover. Receive command specifies behavior during normal runtime, so it can validate a command, create events, and it can use the persist method to persist those events in the journal. And receive recover specifies behavior during recovery from failure. So we can replay those messages and we can retrieve the previous state and continue processing. Another approach called data parallelism in neural networks means using multiple parallel copies of a network and then use different data set with each of them. When, however, we want to update weights in that network, we need the copies. We need to update all the copies. This is usually done using parameter server in neural networks. But we will use different approach. It's called replication. The same entity is essentially replicated multiple times, and the updates are synchronized with each other. A replication approach is generally used in distributed systems for recovery, read concurrency, and partition tolerance. Similarly to sharding, however, replication can reveal some differences, some trade-offs that need to be done between availability and consistency in distributed system. I think mentioning CAP theorem is in presentation about distributed systems is essentially mandatory, so here we go. It describes the relationship between consistency, availability, and partition tolerance in distributed system. It's still largely misunderstood, as demonstrated on the query above from Kyle Kingsbury's blog. But essentially, availability should mean that every request received by a non-failing node in the system must result in a non-error response. And availability means that, consistency means that linearizability. So operation sees results of all previously completed operations. But it's not really one or the other decision. There is much higher granularity of options that can be considered. But in our previous example, to have the same state on all the replicas, we could either update the weight synchronously after all of them agreeing and acknowledging the same value, which, however, means we need to stop processing inputs. And if we wanted to do this,